As we discussed in the last lesson, really, the only way to get good at simplification of Boolean expressions? Practice! Let's show you just 2 more examples in this lesson, just so we can grab a little bit more practice when it comes to these expressions. In fact, let's try an expression, I don't know, this one may be a little bit much to look at first, but hopefully it'll make sense when the deeper we get into it. So let's say I've got A and B bar and C, ORed with A bar and B bar and C, ORed with, let's see, A bar and B bar and C bar, ORed with A bar, whoops, now let's make that A, and B bar and C bar. Hopefully that all fit in the camera. Now, anything that you see in terms of a red flag, and remember, our red flags mean something's being combined with itself, something's being combined with its inverse, or something's being combined with a constant. The only constants we have available to us, 0 and 1. So, I don't see it. I don't see anything right away. What we can see, though, is that B bar is in every single one of those products. So we can use the standard form of the distributive law to pull out a B bar. So I can pull out B bar ANDed with A and C, or A bar and C, or A bar and C bar, or A and C bar. Okay? Still no red flags. Well, what else could we massage around? What else could we move around when it comes to this expression to make it so that it's possibly a little, well, so something shows up that we could simplify? Well, if you see, these first 2 terms, one has A, one has A bar. They both have C. If we pull C out, we can see A or A bar. Let's go ahead and do that for those first 2 terms. So kind of embedding these parentheses, A or A bar. And then we can do a similar thing for this last term. I can pull out C bar and have A bar or A. Now, and in fact, you know, we've talked about this before, where there's usually more than one path to reach a final simplification. If I had swapped these 2 terms, now let's see, if I had swapped these 2 terms through the commutative law, so this product swapped with this product, instead of pulling C out, I could have pulled A out of the first 2 terms and A bar out of the second 2 terms. So really, the path we're taking just happens to be the path we're taking. Now, we do have a red flag showing up, don't we? We have something ORed with its inverse and something ORed with its inverse. Turns out it's the same thing. There's in fact 2 ways we could do this. I could pull A or A bar out of this product and pull A bar or A out of this product, pull it out, and get A or A bar ANDed with C or C bar. But that's not what I'm going to do. What I'm going to do instead is see, I've got something being ORed with its inverse. What happens when you OR something with its inverse? You get 1. Again, here I have something ORed with its inverse. I get 1, all right? Now I have a glaring red flag, right? There's a constant that has showed up here. This constant, well, anything ANDed with 1, always itself. So this becomes B bar ANDed with C or C bar. And then we once again have something being ORed with its inverse. That becomes 1. This becomes B bar ANDed with 1. That's just B bar. And so the final simplification, wow, the final simplification, I have started out with 4 3-input products, ORed together with 1 4-input OR gate. That's a lot of gates. In the end, just an inverter. That all can be taken care of with an inverter. Now, there's something else to kind of see here. And if you're familiar with this idea of 1s and 0s and the patterns of 1s and 0s, you'll see that, yes, once we get to this second step here, this inside of the parentheses has a unique pattern. What it's saying is, if A is a 1 and C is a 1, or if A is a 0 and C is a 1, or if A is a 0 and C is a 0, or if A is a 1 and C is a 0, then everything inside the parentheses is going to be 1. Well, it turns out there's no other pattern of 1s and 0s that A and C could possibly take on. So therefore, it has to be 1. This case, this case, this case, this case, whatever A and C are, it has to be one of these. And so exactly one of these products is going to be 1, and since there's a 1 inside of this OR, inside of this 4-input OR gate, we're going to have a 1 there. We just did it using Boolean identities from here down. So there you go. Let's try one more. All right, now this next expression, well, it may not be as obvious as the previous one, but let's go for it. I've written it down because I can't remember it. Let's see, how about A ANDed with C, ORed with A ANDed with D, ORed with A ANDed with C bar and D bar, ORed with A ANDed with B. Wow. There really isn't any red flag showing up there, is there? Well, we do have an A in every one of those products. So we have the 4 products that are going into a 4-input OR gate. And A, and none of them are inverted, because if one of those were inverted, we can't pull out an A bar with an A at the same time. All 4 of those A's don't have a bar over top of them. So I'm going to go ahead and pull out that A. Pulling out that A is going to give me C or D, or C bar and D bar, or B, right? All right. Now, there are a couple of ways we could do this. First of all, do you remember we had an expression, or excuse me, a property that A ORed with A bar B is equal to A or B. Do you remember that one? Well, we have that kind of here, don't we? If I look at these 2 terms right here, and I substitute D for A, which means D bar is substituted for A bar, and then C bar is substituted for B, this guy is actually equal to D or C bar. So those 2 products, and D really is a product, it's just a product with only one input. D ORed with C bar D bar is the same thing as D or C bar. Now let's bring down the rest of what's inside the parentheses and also bring down the A. So then now we've got this moves to this once we apply this rule right here. The other thing that we could do is use the commutative law. And the commutative law says I can take these 2 terms and swap them around. All right. Hopefully you see the red flag at this point. We've got something ORed with its inverse. All right. Something ORed with its inverse is always 1. So we get 1 or D or B. Of course, don't forget our ANDed with A. Anything ORed with 1 is 1, right? A 1 goes into an OR gate, a 1 comes out of the OR gate. So we've got A and 1, which is equal to A. All right. Well, cool. There's another way to do this, though. And this other way is very different than the application of this rule. What I could do is start with this guy. In fact, let me go ahead and bring this one down. I'm going to put a little line here. We're going to bring this guy back down here. So we'll have A ANDed with C or D or C bar, D bar, or B. Okay. Now, this may not be obvious to somebody who is just starting out in simplification, but it turns out we have an application of De Morgan's theorem, one of De Morgan's theorem's forms in this expression. Remember, what I've got is there were two versions of De Morgan's theorem. One said A or B, the inverse of A or B is equal to A bar ANDed with B bar, right? The other form said that the inverse of A and B is equal to A bar or B bar. The way that worked was I can distribute the bar to the inputs as long as I change the operation. I can distribute the bar to the inputs as long as I change the operation. Well, look at this guy. I could actually apply this backwards, right? The other way around. Instead of distributing, I could pull the bar out. Look at this C bar and D bar. C bar and D bar. That looks like this form, right? If I go backwards and make it A or B inverted, I get A ANDed with C or D ORed with C or D inverse, the inverse of C or D, or B. All right. Now, the commutative law says I could also just simply put parentheses around C or D. And look at this. One step earlier, we got something ORed with its inverse. This is just by an application of De Morgan's theorem. I've got something ORed with its inverse. What happens when I OR something with its inverse? That's going to be equal to 1. What happens when I OR 1 with something? That equals 1, which equals just A. And so our final result, no matter what path we took, is simply that, gosh, once again, I've got 4 products and one 4-input OR gate combining all of these signals together. All of that filtered its way down to just a wire. Just A is driving whatever. As long as A is true, what we're looking for, this expression right here, it's true too. All right, hopefully the 3 examples from the last lesson and the 2 examples from this lesson will give you an idea of how to slowly but surely move your way forward through simplification of these Boolean expressions.